Just ew. Yesterday we did the one box pushing on another box thing, right? Yes. All right, so I have set this up. All right, so is this a simplified version of the picture? So we saw, I hope clearly, that it was accelerating this way. I'm putting the arrow where the acceleration is, like on the pulley, because the weight was accelerating downwards, but the cars were accelerating or up the track. Does that make sense? And although I wanted to draw it just like that, I was drawing it just like that from my vantage point, but obviously it's reversed for yours, sorry. I could probably work out flipping this around, maybe. Maybe I could work it out. And the answer to that is, yeah, no, it won't. Well, flip to one thing, that does mean nothing. So we're okay with this, right? I don't have to draw, all right, good. The only way this mass accelerates downwards is under one condition: the forces are unbalanced, right? It's the only way. So raise your hand if you think the tension in this string is greater than the weights. Same as the weights? Less than the weights. All right, there we go. So that's the only way it accelerates, is if the tension in the string is less than the weight. I'll exaggerate that a bit. I'm trying to draw it so it's perfectly horizontal. And in your lab, the system accelerated this way as well. I asked the same question. Tension in the string, equal to, less than, more than the weight that you're hanging. Has to be less, right? Same conditions apply, but it still has to be less. If this mass is accelerating downwards, the weight has to be less than the tension. Some of you think that under this condition, the acceleration is going to be like G. It won't be. This is a Newton's third law question. I want you to set this problem up, meaning I want you to think about all the forces acting on this car and all the forces acting on this car. This is called a modified Atwood machine. And I want to show you why, when you did your lab, you should have found a slope that was not equal to the weight that was hung. We're going to find out why right now. So, although you did your lab, and I showed you how to use a computer to find out what that slope was, most of you should not have found the weight that was hung. I don't know what you did find, but you probably shouldn't have. And let's see why. Set each mass up. Do the free body diagram for the car on the track, and a free body diagram for the weight that's being hung. When you're doing this, pay attention to scale, please. Right now, so if it were me and I was trying to obey what I told you to do, which is paying attention to scale, I'm going to start with an arrow downward here to be the weight that is hung from the side there, so something like that. Of course, if you did the weight of the cars and you tried to pay attention to scale, you probably have an arrow that should be like huge, right? The car's 500 grams. Without any weights on it, you probably hung on it 20 grams. So I probably can't even see the weight of the car if I wanted to keep them to scale. Does that make sense? Similarly, the normal force, probably way too big. Again, if you're trying to keep it to scale. But here's the scale I want you to focus on. We know the upward force here has to be less than the weight. That's the only way that we have the mass is accelerating downwards. This size arrow has to be the same as this size arrow. They are the third law pair. And for right now, I don't care about the up and down arrows. They're not causing the car to accelerate. I only care about the left to right arrows. You guys follow me so far? All right. In these problems, you're supposed to decide whether it's a first law or second law problem. And right now, we are preparing for your next test, right? When we do problems like this, in my head, this is in preparation for your next test, which is probably this question, right? The one in front of you with lots of objects on there. We're doing it one piece at a time. So right now we're doing the easiest version of this with the track nice and level and only one weight hung off the edge. This is the easy version of this problem, and this is the harder version of this problem. But they are the same problem. They're a modified Atwood machine. Atwood machines are machines in name, really. They're about teaching inertia. That's what they're really about. And that's what we're doing here. both of these objects are going to have a Newton's second law applied to them. But one of them is accelerating in the x direction, and the other one is accelerating in the y direction. Yesterday's problem with the two boxes, they accelerated in the same direction, right? They were horizontal on the ground, and they were accelerated by a single force. These two are accelerating in different directions. You guys see that okay, right? Your next question, and this is something you need to add to your series of steps. Your next question is to ask yourself, do they have the same acceleration? In a multibody problem, we have to ask that question. We didn't have to ask that till now, but we didn't have multibody problems until now. So now that we have a multibody problem, you have to ask, do they have the same acceleration? What I'm really asking you is the motion of this object directly related to the motion of this object. Now, to answer that question, just ask yourself something simple. If this car moves 10 centimeters this way, how much does this move? Does it move the same? Because if it moves the same, then they have the same acceleration. If it moves different, then they have different accelerations. So what do you think? If the car on the table moves to the left 10 centimeters, will the weight that's hung move downwards 10 centimeters? I think that's pretty reasonable, right? Unless the string starts to stretch or something. If we're talking about just simple string, it should be the same. So add that to your list of steps. After you've drawn your free body diagram, after you've decided whether it's a net force problem, MA, or net force equals 0, ask yourself, if it's a second law problem, do your objects move the same? Then do this. Choose a direction for positive that is common for both. You want to get these right? Choose a direction for the acceleration that is positive for both. I'm going to make down positive for the weight that's here, and I'm going to make to the left positive for the weight that's there. Choose a direction for positive that is the same for both. All right. Tension equals mass of the car times A. Pretty easy. Any problem with that? Just like yesterday, kind of? Except tension, not normal force. And then this guy that's hung, mg, minus tension equals mass that is hung times A. We all seen that okay? I don't need the picture anymore, right? I can slide that up and deal just with these two things. Is that okay with you guys? I want to do something with the acceleration here. So I'm going to remind you that at the end of Newton's laws, it tells you something about your system. It gives you an equation about your system. You can use that equation to find things out. I want to find out about the acceleration. That's what I want to find out about. Notice I have no numbers here, and I'm okay. I'm not working with numbers right now. So I'm going to add these two equations together because I can, right? If I add them together, put an equal sign here, the right side will be m mass hung times acceleration plus mass of car times acceleration. That's the right side. The t's cancel out on the left side, right? T minus t is just 0. That's always going to happen in these if you're careful. But I'll have mass that is hung times g. Everybody okay so far? Did I do anything weird? I'm not getting any feedback, so do I have any trouble with this whole process? I am solving for the acceleration, so I'm going to factor out the acceleration. And the acceleration then is, it's kind of complicated looking. Kind of complicated looking, right? Does that look complicated to you? You did the slab, right? You did the slab. How many of you hung 20 grams off the side? How many of you used the car that was 500? Should be almost all of you. you do that? You got mathy skills, right? Could you do that real quick? Point 3769 meters per second squared. When you guys had accelerations, were they that small? I think most of them were, right? In fact, they got smaller, didn't they? As the car got heavier, didn't it accelerate less? In fact, isn't that exactly what this says? As the car got heavier, it accelerated less, right? So our equation supports what you found in the lab. But more importantly, I want you to see one more thing. First, we have found a way to deal with two objects moving at once. This is a simple Atwood machine question. If you look up above this, we have an expression for the tension. Do you see it right there? That's the tension that was in the string. The tension equals mass of car times the acceleration. Well, there's the acceleration. It's really ugly, but I'm going to put these things together because I have to have you see something. So I'm going to put them together. Tension equals mass of car, mass that was hung, divided by mass of car plus mass that was hung, all times g. All right, I just put those two things together. Was your tension constant for your lab? As you changed the mass of the car, did the tension change? Every time, didn't it? Not a lot, but a little bit. The tension was always different. There's a reason for this, something that you should put into your notes. The reason the tension isn't the weight, and the reason why the tension changed all the time, is because the tension is responsible for deciding how much this weight accelerates. In the same way that's responsible to determine how much those accelerate. It's connecting both systems. It's determining the acceleration of the system. So as the system changes, that tension also changes. Even if you never change those masses. You guys never changed those masses. But the acceleration for every single trial was different because you kept changing a different variable. Do you notice how complicated that tension is? All the things that are going into it, that's complicated. So when you change the mass of the car, you changed the way the whole thing operated, the way the whole thing behaved. And it changed the tension. So even though we said the tension should stay the same because you hung the same weight the whole time, it never really did. This is also why it's probably likely that when you guys found the slope of that graph, you found that the tension wasn't what you hung because the tension was always changing. I told you to keep the tension from a weight that was really small because if the mass hung is small, you'll notice that it doesn't change very much. Do you see that that's true? I'm not sure if you can, but it's hard. I'm going to group this a little different, but we said this was pretty much the tension. Right, the weight of the mass that was hung. If you look closely at this, this number is nearly 1, isn't it? It's nearly 1. Do you see why it's nearly 1? Maybe you don't. Mass of car, 500 over 500 plus 20. Is that number close to 1? Pretty close, isn't it? In fact, when you put more weight in there, does it get closer to 1 or further away from 1? Closer. So this was getting closer and closer to the weight hung as long as you kept the mass that you hung small compared to the mass of the car. In fact, the bigger the car got, the closer this got to be the weight. But was it ever the actual weight that was hung? Never. Never. No, it couldn't be. The tension had to be less so the system would accelerate. That has to be true. Now this one's tough. So I want you to bang this around a little bit. I think you guys need a little bit of practice doing this. So I'm going to give you a different one. And I want to see if you can work it out. This one's harder. This is like the next step up in difficulty level. So I'm going to hang two boxes. I'm going to hang them from a light pulley so that the pulley's inertia doesn't interfere. A light, massless pulley. You're going to hear that phrase a lot. We want the pulley to not be part of our problem. So we make the pulley nice and light so it doesn't take any force to get it to turn. That's what we're saying when we say it's a massless pulley. We're trying to ignore the inertia of it. Is there any doubt in your mind about what's going to happen if we let this thing go and it starts to accelerate? So everybody agrees this will go up and this will go down? Okay. I would like you to tell me what the acceleration will be. How fast will this box accelerate? I gave numbers because I thought numbers would be a good way to start. So when we're drawing an arrow representing the 10, you've got to make it 10 units long or 100 units long, right? It represents a force that is 100 newtons. That's its weight. So it needs to fit on the screen. So this is my 100 Newton arrow. That all okay? Now, over here, I have to make an arrow for the weight of the 80. Should it be bigger, same size, or smaller than 100?
Smaller.
Okay, smaller. Message received. That's smaller? Okay. Does the 10 accelerate downwards or accelerate upwards?
Downwards.
All right. Does the 80 accelerate downwards or accelerate upwards?
Upwards.
So I need an arrow on the 80 that's longer than the 80. But that same force, this is the tension force. So I'm going to do something you probably can't do. I'm going to duplicate it. So I have the exact same size arrow. I need to make my tension larger than the 80, but that same tension's acting on both blocks. That's the Newton's third law force. Right? It's just one string. So I need the same size arrow acting on the 100 Newton box. That arrow has to be in between 80 and 100. I don't know how much it is, but it's got to be in between. It has to be less than 100, so this box accelerates downwards. But it has to be more than 80, so this box accelerates upwards. That's why I'm drawing it this way. I'm drawing it to scale as best as I possibly can. I'm also deciding that up for the one box is connected to down for the other box. I'm saying it's going to be the same acceleration. I'm asking myself that question. Are they going to move the same way? In fact, I'm going to draw right on my picture that that's my positive direction. And I'm making downwards positive on the right and upwards positive on the left. I'm saying it's going to be a Newton's second law problem. I'm saying that right now. You guys agree? So I'm going to have 80 minus tension. No, I'm not, because I said upwards is positive. So I'm going to have tension minus 80. Upwards is positive. And that's going to equal 8A. Right? Because this is acting on the 8 kilogram box. What are you going to write on the other side? I did the heavy lifting on the left. Can you do the heavy lifting on the right? I'll have 100 minus T, because downwards is positive. And that's going to equal what?
Tension A.
10A.
I knew that. I knew it. I promise.
I believe you. I believe you. All right, so
I wrote.
that's Newton's laws did that. Now you, the problem solver, probably have to do something with these two things, right? You're the problem solver.
This is making so much sense.
You do this part, right? You see that the tension's negative on one and positive on the other, and maybe add those together, and I get 180 on the left side when I add those together. All right, so I get 100 minus 80 on the left side. Just making sure we're all awake and paying attention. On the right side, do I get a 18A?
Yes.
So 20 equals 18A. That all good? So our acceleration, 20 over 18 meters per second squared, 10 ninths. It's like 1.1 forever, isn't it?
Yeah.
Now, hear me out. I'd love to say you're done. You're not. Go find one of the tensions. Prove that it's between 80 and 100. I don't care. It doesn't matter which equation you use. I would use the one with the 10 in it. It'll be easier. But you can use the one in the 8 in it if you want to make it harder. But go find one of the tensions. I don't care which one.
It's 11.
Yeah.
It's your 11, right?
It is.
You did 10 times 1.1.
I don't want to talk about
I just.
That hurts my heart.
it. I probably would have gotten point 0.11 if I had tried to do it.
It's 10 ninths, right? I just thought there's a fraction. Because it's really not 11. It's 1.1 repeating. But 10 ninth is exact. So I just did that. So tension equals 100 minus 100 ninths. That all good, guys? So what is that? Like 88? 88.9. It's because it's 88.8 repeating. But is that between 80 and 100? Works out? All right.